So hello, in this video we will be covering the part 7 of the CMP 1002 Object-Oriented Programming lecture. Today we'll be talking about the copy constructor, then follow it with the SmartPointers, and then within the SmartPointers we'll be talking about something called the reference variables in order to make some parts of the SmartPointers clearer, I can say. Okay, to start with, this is something that we have briefly talked about in part 6, the copy constructor. We have seen that in some cases the classical default constructor or the one parameter constructor, any other constructor that we have utilized is not going to be used. Instead, C++ is using another special constructor I would call called the copy constructor. This is used when you are going to be initializing an object from another object of the same class. So the prototype of this kind of copy constructor goes like this: name of the class, then you open the parameters, you open the parentheses, and you only take a single argument whose type is const, name of the class, and there's this funny thing, this ampersand symbol in front of the argument name. Argument name, you can just pick whatever you like, it doesn't make any importance at all, but you have to make that there's an ampersand in front of it to notify that this is a reference variable. So normally all classes have a copy constructor, and those default copy constructors, those system defined copy constructor, is just copies all local fields one by one. However, when you are allocating any heap objects within the class, then you are required to write down a user defined copy constructor. As regular constructors, copy constructors are supposed to be public. I mean, well, I think this goes without saying, but if you're saying like, can we just make it private or protected? Yes, of course you can do that. But if you set them to be, set the copy constructor to be anything other than public, then it means that you cannot make a copy out of this class. You are prohibiting the system to making an object out of a copy object from this class. So, this was the like a brief example based on our previous example, this tank example. There were this tank class, and we have defined a couple of objects out of this tank class in the main. There is the 5th division tank, which is calling the one parameter constructor, and there is the 4th division tank. Since it's not getting any arguments, it's gonna be calling the default constructor. Then when we are using this inflict damage function, a function that takes an integer variable and a tank object. So here on the third line, inflict damage 15, 5th division tank, there he's gonna call by value. He's gonna just copy the value of the 5th division tank into another tank object whose name is T. So you are not actually passing the 5th division tank itself, right? So any changes that you have made inside the inflict damage will not have any effect whatsoever over the 5th division tank object. But then how does the C++ continues? It just calls the copy constructor and then copies everything that is recorded inside the 5th division tank and copies it onto the T object, and then he will do all the things about the T, and at the end of the inflict damage function, that T will be destroyed, will be deconstructed, because it's a local variable of that function. At the end of the function scope, it just doesn't make any sense to just let it live. It will just kill it. So that is a very, very good example of the copy constructor. The copy constructor single parameter should be defined as constant. I mean, you can technically omit the constant part, but if you omit that part, if you don't write down the const, then when you are dealing with some temporary objects, there will be compilation errors. It's a bit of a sophisticated issue. I am not going to go into deeper about this temporary objects, but just make sure that putting a constant in front of the variable type when you're defining a copy constructor. Okay, let's write a copy constructor for our tank class. In our copy constructor, what I want to do is, since there's a single local variable, since there's a local field, this armor rating, I'm just going to copy the armor rating of the main object to the copy object. And additionally, I just want the function to print out constructed tank object dash copy constructor, comma, our armor rating is armor rating. And then I want to, in the main, I want to call the inflict damage function on the 5th division object. This time I'm expecting that C++ is gonna be calling the copy constructor. Alright, so let's go to our code. So originally this was our code. There were these 3 items. There were this 5th tank, 5th division tank, 4th division tank, and PTR 3rd division tank. For our discussion, this is not very important, so I can just remove it, honestly speaking. So if I run this code now, as you can see, the constructors are being called twice, while the destructors are being called 3 times. Because of this copy constructor thing, this hidden copy constructor thing, actually there is a third there's a third call to the constructor, but a copy constructor is actually being called. Therefore, we are unable to see any printouts. So, after these 2 constructors, the regular one and the default constructor, I'm just gonna write down a third constructor who's gonna take a single parameter, which is a constant tank reference variable. I can call this obj. This is like, I think, like a little bit more best practice. Well, you can do whatever you want. And in order to make things a little bit clearer, I'm gonna write it with this armor rating equals obj dot armor rating. So I'm just copying the value of the armor rate, the armor rating value of the object, and then copying it into whoever is calling this function, right? Whichever object is utilizing this constructor, he's gonna set his armor rating to the object's armor rating. Then I will have a printout. I'm just gonna copy and paste it, and instead of saying default constructor, I'm gonna say copy constructor. Armor rating is armor rating. So now I have overridden the the system set copy constructor. Now let me run this program. Here now, you are seeing 3 constructor calls. Well, I mean, there were also always, even before there were 3 constructor calls, but one of them was hidden to us. There were, let's say, 3 printouts. One using the 1 parameter constructor based on this line, as you can see. The second one is calling the default constructor using this line. And the third one, when I am actually calling this inflict damage function with this 5th division tank object, he's gonna call the copy constructor. He's gonna call this constructor, right? Therefore, I'm seeing the copy constructor armor rating is 20 here. Since in the inflict damage, he's taken 23 amounts of damage. 20 minus 23 is minus 3. So at the end of this at the end of the inflict damage function here, this local tank object called T is being destroyed. And at that moment, his armor rating is minus 3. Therefore, you see a destructed tank object armor rating is minus 3. So this function is finished now. So I have returned back to the main function. And at the end of the main function, since these 2 things are stack allocated local variables, this 5th division and 4th division tank, they are being destroyed again as usual. So that is mainly a very simple example of using the copy constructor. So when C++ uses the copy constructor, the example I have given you is one of them, but there are other cases where the C++ automatically uses the copy constructor. The first one is when an object of the class is returned by value. So if you have a function and the function's return type is actually an object, that object's copy constructor is being called when this return value is being generated. That's one use case. The second use case is what we have seen here in our previous example, when an object of the class is passed to a function by value as an argument, like this. Void some other function, some arguments we don't care, but at the end there's one of the arguments is an object of the class, the same class. Then the copy constructor is being called. Third, when an object is constructed based on another object of the same class. So I have this tank, 8th division tank 40. I have made an object, a regular object. Then I am making another regular object called 7th division tank, but instead of saying like 7th division tank open parenthesis some number, I'm just saying tank 7th division tank equals 8th division tank. So in this case, he's gonna call the copy constructor of the tank class, and he's gonna get the 8th division tank as the input, and he's gonna construct the 7th division tank object based on the values of the 8th division tank. And the fourth one is when the compiler generates a temporary objects, which I'm not gonna be covering that much. If you're interested, I think there are pretty good resources over the internet or in other books regarding the temporary object concept. Okay, so let's now continue with the smart pointers. So smart pointers are basically pointers with automatic dynamic memory allocation, like helpers or system. So they have been introduced in C++ 2011, C++11. Basically, instantiating objects in the heap via the new new operator have potential memory leak issues. If you remember, one critical problem here is if you instantiate object via the new, you have to write down a delete function correspondingly. Otherwise, you will have a memory leak issue. So in cases that you want to have automated the allocation of these heap allocated variables or objects, then these smart pointers become very, very useful. There are something like a wrapper templates around called smart pointers, and they are being like wrappers around classical pointers. There are variation of the smart pointers. There is no single smart pointer class. There are 4 of them actually: unique pointer, shared pointer, weak pointer, and auto pointer. I am not gonna cover the auto pointer because it was introduced in C++11, if I'm not mistaken, but then they realized that this is a bit problematic. Instead, they wanted to replace it with unique pointer, and you were always also able to use auto pointer before C++17, but in C++17 they just said like, okay, this is causing a lot of problems. So all of the required functionality is now replaced with the unique pointer, and unique pointer is much better in many aspects. So they just completely removed it, deprecated it at C++17. So I am not gonna cover the auto pointer, so don't use it, basically speaking. Okay, what are the differences between these 3 things? The unique pointer basically says that only one unique pointer can refer to a given object. No more than one pointer can refer to the same object. If you want such a thing, then unique pointer is your guy. Shared pointer, multiple shared pointer objects can refer to the same shared object. However, the good thing about the shared pointer is he is gonna manage how many different pointers are pointing to the same object. He's gonna count their numbers, and that's gonna be quite useful very soon. The third one, the weak pointer, it doesn't work on its own. It's like while you have an item that is being pointed by the shared pointer, some weak pointer can also be able to refer to that object. But weak pointer weakly manages how many items access this object, so it's not gonna increase the count in the shared pointer, basically speaking. I'll come to that later when I'm going to talk about the weak pointer. So let's look at the unique pointer. As I mentioned, the main idea is a wrapper making sure that only one pointer can refer to a particular heap allocated object. That's the main idea. Yeah. So instead of writing like this, like the first line, like opening up any heap allocated object using the new operator, so new tank 30 opens up a tank object in the heap. Then I'm taking the address of that object and putting that address to the pointer called PTR 3rd division tank. If I do that, this is just an address and no one is controlling any access, or no one is prohibiting access to that memory access, so anybody can do whatever they want. And at the end, this is you as a programmer, your responsibility to say to the operating system that, okay, now I'm not gonna use it anymore, so I am deleting that object. This is gonna be your responsibility. But instead, if you follow the second line and call like std : unique pointer within these template arrows tank, write down the name of the pointer, then say std : make unique tank 30. Again, here you are making a tank object in the heap. That part is the same. But now it has been referred to by a unique pointer in the stack. And the unique pointer is gonna make sure that no other unique pointer will be referring to that same object. It is gonna be prohibited. And at the end of the function who has defined this PTR first division tank, that function will automatically, C++ compiler will automatically delete the object referred to by this particular unique pointer, because he's gonna know that only that pointer is able to point to that object. So when that pointer just gets killed, so it doesn't make any sense to keep that heap allocated variable, heap allocated object in the memory, because no one will be able to access it anymore. So let me kill it. So he's gonna call the destructor without you writing down anything like delete. Note that this std : make unique usage also came in C++ 14. It wasn't available in C++ 11. There were older usage, let's say, using the new keyword, but I'm suggesting you to use this one. This is better. Alright, let me write down and let me instantiate objects, a tank object via the unique pointer, and see how the constructor and destructor is being called in the code. So here, this was the way when I would be opening up a regular pointer, right? 5th division tank, new tank 30. Nope, did I make a mistake? I might have made a mistake here. Let me cheat a little bit. He didn't like the name? That's weird. Oh, terribly sorry. We already have an item with this name. That was the problem. Sorry about that. So now I want to open up another object, and this time I want it to be wrapped with the unique pointer. So I'm just gonna say std unique ptr tank ptr what was the name? First division tank. First division tank equals std make unique tank, let's say 45. So now see, my IDE is saying like, I don't know what make unique is, and he's just gonna say like, is it the one from the memory library? So I'm just saying yes, and as you can see at the top, now this memory library is being referenced, is being included, because those make unique and unique pointer, shared pointer, all of those stuff are included in the memory library. So now let me call it, let me compile and run this project. Okay, now 4 items are being called, right? 5th division tank, 1 parameter constructor. 4th division tank, default constructor. PTR 3rd division tank, 1 parameter constructor. PTR 1st division tank, 1 parameter constructor, as usual. Then I have this inflict damage function, which calls the copy constructor. At the end of the inflict damage function, this copy object is being destroyed. Then I am able to see only 3 destructed tank object calls. One is for the 5th division tank, another is for the 4th division tank, and another for the PTR 1st division tank. Because make unique is now able to understand that this is no longer useful, so he's automatically deallocating the object for me. I don't have to do anything special for that. But as you can see now in my code, I have a memory leak because I forget to write down delete PTR 3rd division tank, because it was also a heap allocated object, and this is being allocated by the new keyword. So as the programmer, as the coder, it was my responsibility to call the delete function over that pointer, over that particular object. However, for the PTR 1st division tank, I don't have to do that. The compiler is doing that. If I, for some particular reason, try to delete that thing, then you will see that I will be having a bit of an error because I cannot do that. This is not defined. The delete operator is not defined over the PTR over the unique pointer. Okay, so that's mainly one of the big differences between the unique pointer and regular pointer. Okay, another example, and again using the unique pointer, but this time I'm not going to use these objects. I'm going to use an integer. I will be trying to open up an integer array of size 20 using the unique pointer, and then I'm going to get 10 variables from the input as from the user as an input, and then print out the values back to the user via the std code. I just want to show you like the syntax for writing down an array using this unique pointer, because it's a little bit different. I mean, not so much, but yeah. So in order not to confuse myself, I'm just commenting these lines out for the time being. So I'm gonna say, first of all, std, again, unique pointer, unique ptr, right? But since it's gonna be an array, my type t of the template is actually an integer array. And let's call the variable int array equals std make what am I doing? Make unique. Again, the type is integer pointer. This parenthesis is completely nonsense. Then I'm gonna say 20 to notify that the size of the array is 20. So now he has allocated 20 integers in the heap, and the address of these, the address of the 0th element of this array is now being kept inside this unique pointer called int array. And at the end of the function, since this is a local variable and only this particular pointer can refer to that memory space, at the end of this main function, that array will be deallocated automatically. I don't need to do anything else. So let me read some values to this array. Int, let's say int index equals 0, int index less than 10, int index plus plus. std code, int array, int index. Oh, what am I doing? And I'm gonna say std code then I will have another for loop for printing these values to the screen. This time I'm gonna use, as you might be guessing, code, and up. Now I have to give him 10 numbers, some positive, some negative, some small, 3, 6, 8. Okay. So the 0th number is 67, first number is 5, 2 minus 9, and it goes on and on and on like that. So at the end, as you can see, the usage is not different. It is as if I have opened up a memory space in the heap and referring it via a regular pointer. The syntax is the same. That's another neat thing about the unique pointer. The syntax is not changing. Only the definition looks a bit more sophisticated, but the usage is the same as the pointers. But now I don't have to deal with anything like a delete int array at the end of the main, because, you know, he will just do it automatically. Okay. So let's continue with passing unique pointers to functions, because there's a bit of an interesting thing here. If I were to actually gonna pass an object, a tank object, to this inflict damage function by reference, what I'm supposed to do is I have to rewrite this inflict damage function so that it doesn't take any direct objects, but it takes a pointer to an object, like this tank star t. And then I have to say, like, instead of t dot sustain damage, I have to say t dash arrow sustain damage to say that just go to the object that has been whose address is given in t. And this time I am just gonna give the pointer object the pointer variable where the address of the actual object is being kept to the function. So this was how I normally use it if I'm using a classical pointers, right? So I'm gonna say, instead of 5th division tank, I'm gonna say PTR 3rd division tank, but I have to make a copy of this inflict damage function, a version where the second parameter is not a tank object but a pointer to a tank object. Let me again first of all comment this line out and see how does the constructors and destructors are working in this case. So we can delete this part too to decrease the clutter. Okay, as you can see now I am not calling the copy constructor, because now I have 3 objects: 5th division tank, 4th, and the object that has been referred by the PTR 3rd division tank pointer. And now I am just giving him the address, right? I am not making any new objects. I'm just passing the address of that object to the function. And the function is now getting the address and then just accessing the object via this address and then call the sustain damage function. Therefore, there is no 4th object being created. And as you can see, consequently, the 3rd division object started its life with an armor rating of 30, but then he got hit with a damage of 23. So 30 minus 23, at the point of being destroyed by the destructor, by the delete function, his armor rating is recorded to be 7. 30 minus 23, 7. Cool. So now let me try to write the same thing with the unique pointer. Instinctively, this is how it feels like I'm supposed to write. I have to change the function, make another copy of the function, but instead of saying tank star t, I'm supposed to write down std unique ptr tank t. And then in the main, I'm gonna just call, I'm just gonna give the pointer of the ptr first d tank, right? This is what I'm normally supposed to do, I think. So std unique ptr tank t. So the function, as you can see, is not giving me any compilation errors. That's perfectly fine. And so I'm gonna change it to 1st division tank, but wait a second, it is not allowing me to do that. So it's saying call to deleted constructor. So apparently this is problematic, this is wrong. I can't write such a line here. I cannot call this function using this unique pointer, right? So this is an error, this is a problematic thing. Okay, this might be a bit confusing. You might feel like the Jackie Chan is feeling right now, like what is going on here, like why it is not working. Okay, when we do this, when we use a regular pointer, in actuality there's an object of tank class tank. When you write down tank star ptr 3rd division tank equals new tank 30, there's an object of the class tank has been created, constructed, instantiated in the heap. And there's a pointer, PTR 3rd division tank pointer, which is referring to that object. The address of the object A is now being kept at the PTR 3rd division tank. When you pass this address to the inflict damage function, the inflict damage function will immediately open up another pointer called T, which is also keeping the address of the same object. So now I have two pointers referring to this same object. But in the unique pointer case, if I again say like unique PTR tank, PTR first D tank, make unique tank 30, there's this new object, let me call it object B, and there's this first PTR first D tank, which is referring to that object B. However, when I'm trying to copy the address to another pointer, in this code example it says UT, when I'm trying to do that, this is illegal. Because this is illegal because of the unique pointer data structure. Unique pointer is just gonna say like, no. Only the unique pointer, the PTR first D tank, is allowed to point to that object. No other pointer can refer to the same object. I am prohibiting it because I am a unique pointer, hence the unique name. Come on. If it wasn't like that, then why should I be calling it unique pointer, right? Huh. Okay, why am I dealing with such a problem? Like, what is the big deal? Why that the first usage is problematic? Let's say this delete thing, I am a very careful person, and at the end of the program, I always say I'm gonna delete all of the heap allocated local variables. I'm very careful, let's say. So, is there any other reason why I am supposed to choose the unique pointer? Well, let me go to this code and let me again call this 5th division PTR 3rd division tank, which is fine and dandy. This is, as I mentioned, very good. And I am a very careful, very good programmer, and I am not forgetting to delete this PTR 3rd division tank. But let's assume that I have given the responsibility of writing down the inflict damage function to a friend of mine, to another coworker, whoever, and then he or she is also unaware of the fact that if I write down this delete or not. So he or she is a little bit hesitant, and at the end she decided to write down something like this, which is, as you can see, no compilation errors, because it is a pointer and I can call the delete operator over that pointer. Now what he's gonna do is he's gonna actually delete my object A within the inflict damage function. But I was already trying to delete it in the main. But the C++ compiler has no way of understanding that who has deleted the object. Is it at the end of this function, is it deleted or not? I mean, you can make a check, like if this PTR division tank is null pointer or something like that. But if you don't do such a check, let's see what happens if I run it like this. Okay, I have these 4 now constructed things. Okay. So the 5th division tank. Okay, maybe let me comment these things out because they are not important for our discussion. So let me simplify things. So there's only one object is being created by the constructor using this line, right? And the inflict damage function at the end, he is actually deleting the object. But since T and PTR 3rd division tank is referring to the same object, that now the address that has been referred by the PTR 3rd division tank is also an illegal address. So this pointer is not now pointing to an invalid address. But he's again is trying to delete something, and at the end of this destructor, if you remember, the destructor is also accessing the value of the object. But at that time, since the object is already being destroyed, there is a very funny, very bizarre looking number here, which is completely wrong. So this is a big problem here. Should I be using the delete here or should I be using the delete here? How can I, like, which of these functions is supposed to be responsible from deleting it? That is another big problem with the classical pointers. But when you are using the unique pointer, since it is the responsibility of whoever is opening up the unique pointer, then it is also clear like where the delete the destructor should be called. Again, a second very important benefit of using the unique pointer. But then you might be saying like, how am I gonna really access? Because if I now go here, and let me comment this part out now. And I want to actually pass this thing as a reference, because I can pass it with a value like this, which is fine. But then this function will be called, right? Because the star PTR first division tank has a type of tank. So it's gonna be the copy, a copy constructor will be called, and copy of the object will be constructed, and it will be destructed. So it will have no effect over the object that has been referred by the PTR first division tank. So how am I gonna call this the object referred by the PTR first division tank using this unique pointer? How am I gonna do that? So one way of doing it by using this reference variables. But before talking about how to do that, let me talk about the reference variables. Reference variables are basically, at their core, new names to old variables. So let's look at this example. I have this number, integer number variable called number, well, and I'm just opening up another variable called x, but this time I'm putting this little ampersand symbol in front of the name of x, which is gonna say that x is actually not a variable, but it's a reference variable. A reference to who? What? The number variable. So basically, they are referring to the same number, but be careful, they are not pointers. They're just two different names of the same variable. So when I write down this std code number and std code x, they will be writing down the same value, 9. And when I say number equals 12, so both the number and x will become 12 because they are the same name, same variable with two different names. And if I say x equals 24, both the number's value and x's value will become 24. So why this is important? Because I can now use the call by reference to a function utilizing this reference variable concept. So let's, for a very particular, very strange reason, I want to change the value of this number to 12, and I want to do it within a specific function. One way of doing it, as you remember, to just pass the address of the variable called number, and the change value to 12 function is gonna take the address, keep it in a pointer, and then say, okay, the value in the referred to in the pointer will be changed to 12. Instead of utilizing it with using a pointer, I can use a reference variable here by saying like void change value to 12 int ampersand n. Now all I have to do is just give the actual variable. So he's gonna define another reference variable within the context of the change value to 12 function, and since n is a name for the same variable, if I say n equals 12, in actuality, the value of the number will also be changed. Alright? So let me give another coding example using the super classical swap function. I'm just gonna write the swap function using a reference variable as the argument parameters instead of the pointers. Okay. Again, for this discussion, I don't need these things, so I'm commenting them out. So normally we were saying like, assume that I have these two things. First number, whose value is, let's say, 9, int second number, whose value is 5, let's say. And what I want to do is, first of all, write their values to the screen. Then I'm gonna call a swap function, which I'm gonna write very soon. So this is normally what I'm doing. And my swap function should look like this if I write it with a classical pointer structure. Terrible, sorry. What did I do? Oh. So really, we have achieved of changing the values of these two things with the swap function, but we have utilized the pointers. So I did pass the address of both the first value, the first number and second number, and then via the address they were able to change it. But as you remember, we cannot do it with the unique pointer things. So how am I gonna use it? So what I'm gonna do is I'm gonna write down a version of the swap which is now using the reference variable. So instead of writing down %a, I'm just gonna star a, I'm writing down %a and %b. Now in this case, a and b are actually names for the same variables. So now I'm gonna delete these ampersands, and then when I run this code, it will work exactly like the previous version. It will in a functional point of view. So the values of the first number and second number will be swapped successfully, and this is going to be another version of call by reference. But the thing is, now I'm actually naming two more variables inside the swap, a and b. I am not passing their pointers. Be careful, they are two different things. So now I'm utilizing the call by reference. There's another example here, which is gonna be a bit more sophisticated version of the previous example. Instead of writing down a swap function for the int, what I want you to do is to write down a swap function using a function template that takes two reference variables of type t, and whatever the type, it could be double, it could be char, it could be whatever, okay? And in the main, I want you to use it with two int, two doubles, and two char values. A little bit of variation. We have already covered it in the function template lecture. So this is going to be a bit of an interesting example. Okay, so the thing is, eventually, while I have utilized this function on the top and tried to access it using the inflict damage 11, PTR 3rd division tank, so this two couple is wrong, because I cannot do that because of this unique pointer structure. However, if I change the function so that this function is now getting a reference variable, then this is fine, because there are no two pointers being referred to the same. There are no two pointers referring to the same object. So now C++ will understand when to kill this function, when to kill this object, because the original pointer is within the main function. So he's gonna keep track of that, and he will just destroy the object referred to by the unique pointer at the end of the main function. He's not gonna call the delete at the end of the inflict damage. He's gonna know to call that at the end of the main. Yeah, this is a bit confusing. I am completely aware of that. Don't get me wrong. It's not something super easy to grasp at the first instance. So I strongly suggest you to play around with this reference variable stuff so that you can understand and try to make some mistakes and see what kind of compilation errors are being happening. Okay? Alright, so let's continue with the second smart pointer, the shared pointer. So the shared pointer is again a wrapper around this object that has been declared in the heap, and there's going to be managing the deallocation automatically. But the main difference is that the shared pointer will be counting how many pointers are referring to this object at any given time. So multiple shared pointers are allowed to point at the same object, unlike the unique pointer. If this count value becomes 0, then the shared pointer will be calling the delete operator, and then the destructor will be called, and then the object will be actually destroyed. So how you write a shared pointer? Actually nothing so different from the unique pointer. You're only changing the name from unique underscore PTR to shared underscore PTR. And on the right hand side, instead of saying make underscore unique, you're gonna be writing make underscore shared. Okay, let's compare the unique pointer and shared pointer, how they act differently. So the main difference comes into play when you are trying to have another pointer referring to the same object. As we have explained in a lot of detail, this code is wrong. You cannot compile it because UT is unable to refer to the same object because the PTR first tank is actually a unique pointer. But if I write the same code using the shared pointer, the PTR second tank is a shared pointer, is referred by a shared pointer, and the inflict damage function is now having a shared pointer object. Now we have this new object, object C, and this PTR second tank is referring to that. When it has been passed into this function inflict damage, there's a new pointer will be created as ST, and ST will also be referring to that same object. But the good thing about the shared pointer structure is that he's gonna count how many pointers are pointing at the same object. And the good thing about this thing is, at the end of the inflict damage function, as you know, the ST is a local variable, similar to int damage. So ST will become null and void, it will be destroyed. But be careful, the pointer will become destroyed. At that moment, he's gonna decrease the count of this shared pointer from 2 to 1. So since this number is not 0, he's gonna say, aha, there is one more pointer pointing at this object. So if I call the delete, I'm gonna break the thing, right? The other pointer, that poor pointer, will be unable to access that object. So I shouldn't be doing that, and he will not call the delete. But when he comes back to the main function, this count value will become 1, and at the end of the main, it will again be decreased by 1, and it will become 0. When it becomes 0, he will understand that no other pointer is referring to this particular object, so it is safe to delete it from the heap. And that is, as you might be imagining, a super powerful thing. So we have a couple of helper functions in the shared pointer. Actually, we can, with this use count function, we can just get how many objects are currently referring to any particular object wrapped around by a shared pointer. We can call this reset function manually by saying like, okay, I don't want this pointer to refer to this object anymore. And if it is the final pointer referring to the object, then the object will be destroyed. Normally, unless you do that, unless you specifically want to do that, you don't do that, but there is a capability. And the third function is a function that returns a boolean value. It's gonna checking if this is the only pointer referring to this object. If it is, then it's gonna say true, otherwise it's gonna say false. So you can write things like, if this is like unique, then reset it, something like that, if you need it. All right. Let's make an example with the shared pointer. So here in the, I want to write down an inflict damage function, which is gonna take one integer as always, and it's gonna take a shared PTR called ST. And this shared pointer, this inflict damage function, what I wanted to do is to print out the address of the tank object by this shared pointer, the address, as well as the number of pointers referring to this object using this use underscore count function of the pointer. In the main, I want to make an one heap allocated tank object using the shared pointer, and then I'm gonna call the use count function before calling the inflict damage function, and then I'm gonna call the inflict damage function. Then I want to observe what is being printed out to the screen. So the swaps are unimportant at this time, as well as this part. We're gonna be using them. In order not to get confused, I'm gonna remove the third division tank things up, and also I'm gonna remove this fourth and fifth division things. So this guy is now gonna be, oh sorry, first of all I am gonna rewrite this function But this time, this function is gonna take a shared pointer called ST. ST sustained damage. And in the main, this is again is gonna be a shared pointer object. Or to show you the difference between these two, let me write it here. Shared PTR, PTR second division tank. Make shared, and this is gonna be a much stronger tank, let's say. And in this case, I'm gonna say PTR second division tank. But this is not all. So the example says inflict damage function should print out the address of the tank object as well as number of pointers pointing at this object using the use count function. Okay. So std code the object whose address is st has been referred to by st dot use count number of pointers. So I'm gonna write the same thing, but this time, as you remember, there is no such thing as st here. So I'm gonna say PTR second division tank, and same goes here. Did I miss anything? I guess not. Okay, so in the main, I am having two objects being created in the heap. One of them is referred by the PTR first division tank, which is a unique pointer, and second one is the PTR second division tank, which is a shared pointer. So two 1 parameter constructor calls are happening, one with 45, one with 56, because of these two lines. Then, after the shared object has been called, the address is apparently 0x3148C, and this has been referred by one number of pointers, because that is what it is. When you pass it to the function, this function will make another pointer called st, which is referring to the same memory space, as you can see here. The same we are referring to same address, and now he is aware of the fact that two pointers are referring to the same object, right? With the use count function, I am able to get the value of how many pointers are referring to this object. And the good thing about this is that, as I mentioned, at the end of the inflict damage function, he's going to decrease this value by 1. He's going to destroy the local variable st. But since this value is not 0, he will not destroy the object itself. That would be the job of the main. When the main is being finished, this number will again be decreased by 1 to 0, and then he's going to call the destructor of this object. That's pretty neat, I would say. And I think it's very, very super flexible thing. Unique pointer has its uses. If you make sure that no other people is going to be referring to that thing. No other pointer should be referring to that thing. But shared pointer is your guy when you really want multiple functions to refer to the same object as if it is the regular pointer. But you want the system to keep track of how many things, how many pointers are referring to that. And who is going to be responsible of deleting the actual object without all this delete mess. And without going into detail about the reference variables. But again, this is a versatility. There are cases where unique pointer is better suited, when there are cases where the shared pointer is more suited. Last thing is the weak pointer. So the weak pointer is main idea, but there is no such thing as you cannot make an object and directly refer to a weak pointer. No. You can only refer to a previously instantiated object by a shared pointer. So in this example, I am having another object, and this PTR 9th division tank is actually referring to this class, referring to this object, sorry. And I think I make a typo in the second part. I'm saying like, oh no, there's a WPTR 9th division tank in the second line. Yeah, it's a bit weird, I know. I just want to show like they are referring to the same thing actually. But the interesting thing is that in the second line, when you open up a weak pointer, it is gonna refer to the same object, but it is not gonna increase this value of the shared pointer. He's not gonna be aware of the fact that another pointer is referring to that, because it's not gonna be the responsibility of the shared pointer to check like this is like unimportant guy, kind of. Okay. So the weak pointer, you cannot direct access to object managed by a weak pointer. That's an important second part. You can only do that by using this lock function. You can just call the lock function, and the return type of this lock function is a temporary shared pointer object that is that is referring to that same object. You can also, but instead of using the lock and getting a temporary shared pointer object, you can always use the useCount function. It also exists in the weak pointer, and this guy can check how many shared pointer objects are being referring to this object. But be careful, he's not count himself, because he's a weak guy, he doesn't count. And finally, there's an important, very important function, like if this object referred to this pointer was already deleted, by calling the expired function. As you can imagine, this expired function is extremely important, because when all the instances of the shared pointer are being destroyed, that object will also be destroyed. So the system will not care if there's a weak pointer referring to that object. So it's going to be your responsibility to check if the object is already being expired or not. Again, this is useful in some scenarios, but it is less powerful than the shared pointer. But I'm hesitant to say less powerful. What I would be saying, like less common maybe usage would be a better choice of words, because all three of them are useful in their specific cases, in their specific scenarios. Okay, so that would be it for this week. So we have covered the smart pointers, we have covered the copy constructor, and we briefly looked at the reference pointer. And we have said that there are these three versions of the smart pointers: the unique, shared, and the weak. Each one of them have their own uses. Whichever you want to use completely depends on the instance, what you are trying to achieve. The syntax is not super strong, super complicated. It may look a little bit longer than the classical pointer, but well, I mean, come on. And there are these specific functions, helper functions, this use.count, use_count, things like that, that are especially useful in the shared pointer and the weak pointer. So next week we'll be covering the vectors, iterators, and the auto. Thank you for listening. I hope you enjoyed it and you have learned something. I hope it's not a very long video. So see you next time. Bye bye.